right, so with our symmetry of graphs and equation lesson, we're going to focus on these three types of symmetry. So again, we're going to try to figure out when we are given an equation, we're given a point, when we're given a graph, and they can have more than one kind of symmetry, but I drew you three examples that do not. This first example of a parabola only has y-axis symmetry because the y-axis is cutting it in half. And it looks like you could fold it up like a butterfly and both sides would be the same. Same thing with this x-axis symmetry. I can fold it up on the x-axis and it will look the same because those are reflections. That the left and the right are reflections of each other. But when you look at origin symmetry is not a reflection. It's a rotation. And again, it can be in quadrant 1 and 3 and look like you can take quadrant 1 and rotate it around and make it 3, or it can be in 2 and 4. But sometimes there may be something in all the quadrants, so you still have to think about, will 1 become 3 or will 2 become 4 for it to have origin symmetry. So we're going to do a visualization first with just one point, and then we're going to look at some graphs that are like these and say, do they have all kinds of different symmetry? Some graphs can have more than one kind, and these don't, but some can. All right, are we good? All right, so first thing we're going to do is we're going to take some points, and we're going to look at just plotting that point, the original point, and then after we plot the original point, we're going to do these different types of symmetry to see what happens when it has that kind of symmetry. So I started out with the point in quadrant 1. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. All right, so I'm going to plot the point 3, 4, which is over 3 and up 4 in quadrant 1. This is the original point. I'll tell you what, instead of putting that, I'm going to put the point next to it. Now we want to flip that over the x-axis. So as we flip it over the x-axis, it has to stay the same distance from the axis you're flipping it over. So how far is it to the x-axis? 4. So we'll do 4 down. Everybody agree? All right. So now this is our new point for part A, and our point now is at 3, negative 4, and this was our x-axis symmetry. What happened to my point? When I brought it down here, what happened to it? Something became a negative. Okay. So, do you think that would happen if, no matter what? Yeah. Well, we'll try another one a little bit and see, make sure. All right, let's do y-axis. So, right now, how far is this over to there? 3. Then we're going to come over here, 3. And so that's going to be part B's answer. It's now at what point? Negative 3, 4. Negative 3, 4. This was our y-axis symmetry. Now go back and look at the original problem. Was 3, 4. What changed? The x changed and made it the opposite, right? Well, when I did the x-axis, the y changed. All right, now let's do origin symmetry. Now with origin symmetry, you kind of have to think of it like it's got to flip over this origin point here in the middle. So for that to happen, what do you think is going to happen to the point? Okay. In this third quadrant. All right, so if I come over negative 3 and down negative 4, how am I absolutely sure that that's all that happened to it? Because sometimes numbers switch around, not staying in the same places. Sometimes it's not just things became negative, but sometimes the two numbers actually flip-flop and they become the other position. How am I sure that this is where it ends up? And this is the key. Does it make a straight line? Uh-huh. So you'd know for sure that's right. So this has origin, and our point now is at negative 3, negative 4. So it changed both of them. Well, let's try number 2. Do you think it's going to make any difference no matter what quadrant I start in? Well, maybe, I don't know. Let's see. So the original point is over negative 2, up 1. This is our original point. So now we're going to flip it over the x-axis. So it's got to go down to go over the x-axis, right? Down how much? 1. So now this is the answer to part A. It's now the point -2, -1. And that was my x-axis symmetry. Now on our first question, when we flipped over the x-axis, the y changed. Did that happen this time? Everybody agree? All right. Let's make a note of that. When you have x-axis, the y changes. And the x stays the same. All right, now let's flip that across the y-axis from quadrant 2 over to quadrant 1. How far away from quadrant axis do I need to be in quadrant 1? How far over? Correct. So it's 2 over to the point on the y-axis, so it's got to be 2 over on the other side to be symmetry. And so this is our part B answer for y-axis. And our point now is at 2, 1. What changed? The x changed to the opposite. It was negative, now it's positive. Over here when we did y-axis, it went from positive to negative. So the x changed there too. So it seems like the rule for y-axis symmetry is that the x changes to the opposite and the y stays the same. Okay. So if I flip this across the origin, it has to end up here. Everybody agree? So that's part C for the origin, showing that it went to -2, excuse me, -1, to -1. From the original point over here, at -2, 1 to the point over here, 2, -1, did everybody change? Because that's what we determined over here was going to happen, that our 2 positives became 2 negatives when they went to quadrant 3. Well, that makes sense because when you go from quadrant 2 to quadrant 4, what's negative switches, doesn't it? So both of them switched sign. One went from negative to positive, and the other one went from positive to negative. And so our origin symmetry problem is the fact that they both change. Now, I threw in question number 3 because it's on an axis. So I thought it would be interesting to see what happens if you have one on the line. And then we may talk about number 4 in a different way. So the original point is 3 on the y-axis down at negative, right? Down to -3. So that's my original point. Now if I flip that over the x-axis, where will it be? 0, 3. All right, so this is part A, thank you, for x-axis. All right, let's see if it fits the rule. The rule says only the y changes to the opposite. Did the y's change to opposite? Okay. Now, what do you do if you want to flip over the y-axis and you're on it? You're your own point, right? It don't change. There won't be any change. It's the same point.
So you don't do origin or nothing?
So this part right here is going to be the original point, and it's going to be part B for y-axis also. It's its own point. If you're on the axis and you're trying to flip over that axis, you can't flip over an axis you're already on. Does that make sense? Because I flipped it from here to there. Alright, so the y-axis is its own self. The original point and what flips over the y-axis would be the same because it doesn't change. You can't flip over something you're on. Now, but I can flip over the origin, can I not? This point also is the origin one. So when you're on an axis, it's kind of different because you can't get 4 different points. Because one of them you're on it, so you can't flip over something you're on, and the other 2 can become the one that it can go to. All right, now, here's the origin, right? Here's the original point. Flip over it. It's the same one as the x-axis. All right, on this last question, I want you to make me the points without drawing it. I want you to use the rules and see if you can come up with, on these rules, how to change that point without graphing it and get each one. So if you know the rules that we've come up with, do you need a picture to do it? No. You should be able to take any point and flip it. So as long as you know what changes, and this is why people mess this up all the time. They say, well, it's x-axis, the x should change. But if you knew what the equation of the x-axis was, you'd know why it's y changing. So let's talk about that a minute. What y number is this on? 0. See, the x-axis is the equation y equals 0. That's why y changes. Just same thing with this one. The equation of the y-axis is x equals 0. If you flip over x equals 0, I'd expect to change my x. And then, of course, this one just changes both because you're rotating. So with this problem, if I change the y, didn't it become positive? If I go back to the original problem and change the x, they're both negative. And if I go back to the original problem and change both of them, it'd be negative 4 and positive 3. Does everybody agree with that? All right. So this is just one thing that helps you to develop the rules. So if you forget the rules for the day of a quiz or a test, you could take a point, flip them around, make your rules, list them down, because I'm expecting you to be able to do some algebra with that. And if you can't remember the rule, you've got to come up with it. And here's a way to learn how to come up with the rule. All right, the second part is the visual part. You're supposed to be able to look at the picture and tell me all the different symmetries it might have. Some graphs might have all 3. Some may not. Some may have none. The key is you should be able to go through one of them at a time and decide what it cuts in half. Or does it look rotated? For example, did the x and the y-axis cut this graph in half? And you don't have to put the points on yours. If you just want to draw a rough sketch and have the picture, it's fine. But the key here is that's what you want to do. You want to say, did the x or y-axis cut it in half? If neither one of them cut it in half, then you want to look and see, did it rotate? That's your key factors. And again, it may be all 3, it may be none of them. It may be 2 of them. Who knows? We have to think it through. So in this first one, I have a parabola. What cut it in half? All right, then it's got y-axis symmetry. Does that make sense? I cut it in half right here, therefore it has to be y-axis symmetry. Right? This falls over there. Does it have x? Does it have y origin? No. Doesn't even go through the origin. All right. If I cut the y-axis or the x-axis in half, will it fold on top of itself? No. Will it rotate around the origin and become the other one? Yes, because this is a sine wave or a cosine wave that's been adjusted some, and it goes through the origin, so it's got a pretty good chance of having an origin. If you rotate quadrant 1 around, it'll become quadrant 3, so this is origin symmetry. So that's what you want to do. You want to first see, did it cut it in half with the x or the y, and then after you figure that out, you look for origin. And if it don't go through the origin, it can't have origin. So it's just a visualization, right? Everybody with me? Everybody ready to go to the next one? I did say you didn't have to write the points down. Last one, what? You mean the one with all the problems we've been working over here? Okay. I thought that was the one y'all did yourself. Okay. You got it all now? Okay. All right. How much more of this one do you need? Anybody need more of this page? We good? Oh, well, that's sometimes what happens. All right, so this is a rational function. A rational function is a graph that has x and y vertical asymptotes, horizontal asymptotes that cut the graph up. We'll be studying those here in a few weeks. But does it cut it in half in any form or fashion? The y? Yeah, if I cut the y in half, the parabola would fold over, and this piece with the bottom would also fold over. Does it cut it in half with the x? No. So this has y-axis symmetry. What about the origin? Well, but it could have origin symmetry if I can rotate quadrant 1 and that looks like 3. Not really. Yeah, because quadrant 1 touches the y-axis and quadrant 3 doesn't, does it? So that's a pretty good clue real quick. What do you think about this one over here? Okay, x-axis. Doesn't look like the y-axis will cut it in half and fold, does it? Just the x. How about origin? Nah, it didn't go through the origin. So it only has one kind. So some graphs only have one kind. That's all they have. Now, this first one here is a function. I can write an equation for that. That over there, I can't write a y equal to equation for because it don't pass the vertical line test. So being able to take an equation and graph it in y equals could be helpful because you could look at it and see what it has, but not everything's graphable, which is why we need to be able to also do some algebra, which is what we're going to go to next. Now in your homework tonight, you have some questions that the graphs are already drawn, and all you got to do is tell me how many different ways it has it. For example, how many different ways would a circle have?
No, wait a minute.
It would have everywhere.
A circle that
If what?
its center is the origin.
If the center is the origin, then it might have everything. If the center's not an origin, it wouldn't. But if the center was the origin, it would. So you've got to be able to visualize it. So you got a bunch of graphs tonight on your homework, and some of them have more than one kind. Well, we didn't have that as much in the notes. All right, now we're going to look at the algebra portion. And this is what we're going to be doing right here to prove it, is we're going to replace y's with a negative y to prove it has x-axis symmetry. We're going to replace the x with a negative x to see if it has y-axis symmetry. And we're going to replace both for the origin We'll make a negative x and a negative y to see if it has that. And we have a variety of different equations to work with. So these are what we're doing to prove it. These are the rules that I wrote on the other slide, right? Right? These are the rules. This is negative y, negative x, negative on both. I just wrote it in words. All right, so we're going to have to do 3 separate short little algebra problems to be able to prove it with each one. You have to show work, and you can't take any shortcuts. So we'll start by writing the word x-axis, and everything under that will be about the x-axis work. You'll have 3 columns when you do these, 1 for each test. So I'm supposed to put in negative y when I have x-axis symmetry because the y changes, right? So that means I take out the y and I put in a negative y. Now, in this case, the process is there's 2 things you can do to try to see if you can make it back into the original problem. You either work with a power or you work with a negative 1. And because this doesn't have a power on it, I have to work with negative 1. And what you do is you multiply the whole problem by negative 1 to see, does that fix anything back to the way the question was originally? Well, now my x squared is negative, my y is positive, my 5 is negative. It fixes the y back to the original problem, but it did fix the other 2? No. So this does not have x-axis symmetry because it didn't fix the problem back to the original problem. It has to match the original problem for it to have that kind of symmetry. So the answer to this one is no. So now we're going to do y-axis symmetry. Now when we do y-axis symmetry, we're looking for placing negative x in here for the plane x that we have right now. And that means that I need to put parentheses around it because it's a power. So I go back to the original problem. I take out the x, I put in negative x, and anytime you put in negatives with powers, you have to write parentheses around it so that it gets done correctly. You don't put the parentheses, it doesn't mean the same thing. So what happens when you take a negative to an even power?
It goes even.
It goes even. What does that mean? All right, so it makes it positive. And so therefore, it does away with that negative, and that's the other way of getting rid of a negative in these problems is you can square it out, and therefore it does match the original problem and makes this have y-axis symmetry, which, by the way, this equation of this would be one of those parabolas that goes like this. So now let's prove whether or not it has origin symmetry, because I don't know if it touches the origin or not. Might. So you put in both negatives at the same time. And what I like about origin symmetry is it uses both rules usually, if there are powers in the problem. It'll use how to get rid of a negative and a power, and it'll use how to do the negative over here. So a lot of times you've already known how to do the work, you just got to show both. Always do the power work first. So that turns that into a positive, right? And then multiply it by the negative 1 just to prove that it doesn't fix it. Because we already know it doesn't fix it. How do we know that? We just did that a few minutes ago, so we can just copy that over here, right? No. No. It has to do with where you put the negative in the problem. If you put it in for a power, then you work the power out. If you put it in for something that don't have a power, you multiply it by negative 1. It's not which kind of symmetry it has. It's where is it in the problem. Does it have a power or not? All right, so this problem only had y-axis symmetry, which makes sense because of the kind of question it is. All right. Might actually be opened this way. I said it would open this way, but it opens this way. Y-axis symmetry. All right. Now, this one, even if I solved that other one for y and typed it in the calculator, I could not do that with this one. And I could have done that. I could have solved it for a while and looked at the picture in the calculator. But I'm trying to show algebraically how you do it because not all problems are typed in the calculator. For example, this is a circle equation. And so it's a really short circle equation, but it is a circle equation. And so because of that, I really truly need to know, is it going to be centered at the origin? I don't know. I mean, I guess that depends on if you've ever studied circle equations before. And so if you haven't, then we got to do the math. And to see, is it around the origin? Is it off-centered somewhere else? The math will prove it. So first you start off with x-axis. You put in a negative for y, right? Everybody agree with that? That you put in a negative for y when you do an x-axis? What happens to my negative? Goes away. So because I'm doing a power problem, I square it out. And so the answer to this one is yes. Now I'm going to do y-axis. That means put in negative for x. Guess what? It goes away. So yes, it has y-axis symmetry. Now if it was yes for one of them and it was yes for the other one, that doesn't mean the origin is going to be yes. Because once in a while it's not. It depends on what the equation is. But in this particular case, because we're squaring it out, negative x quantity squared plus negative y quantity squared equals 9, and squaring it out individually did it, then squaring it out with both of them would also do it. So this circle was centered at the origin with a radius of 3. Where did I get that from? Yeah, what's the square root of 9? Pythagorean theorem. A squared plus b squared equals r squared. X, Y, R formulas that we studied earlier. No, the radius is 3 for this circle. Okay. All right, so we're going to look at one more that's a little longer formula. This would also be a circle formula. See, they're not all short, are they? Now, every x or every y gets whatever you're plugging in. You don't just put it in one of them. So when you do x-axis, you're supposed to do negative y. Everybody agree? So I'm going to say negative y quantity squared minus 4x minus 6 times negative y plus 27 equals 0. So I put negative y in for both y positions. Always deal with the powers first. If there's something that's got a negative inside of a power, you want to square that out first. And they're not always squares. Sometimes it's cubed. What happens when you cube a negative? It stays negative. Okay. So this will be x squared plus y squared, and then the minus 4x. But what happens here? Plus 6y plus 27 equals 0. So I fix the squared. It matches the x squared, the y squared, the negative 4x, and the 27 match, but this one don't. Now I can multiply the whole thing by negative. Is that going to fix that? It'll mess everything else up. Well, let's do that to prove it. We're just trying to prove it by trying to fix each one thing one at a time. So now all of them are going to be the opposite except for the one that we want. That didn't help, did it? So the key here is by multiplying everything by a negative, it only fixed the one term that was wrong in the first place before that step, right? Now everybody's wrong but that one. So that really didn't help. All right, you do the same thing for y-axis. Oh, you might have to put these up and down. Sometimes they're long. Plug in negative x's. Plug in negative x and show your work for that. I only have 2 more of these, y'all. This one and one more. So you're plugging in the negative x in the squared and plugging in the negative x with the negative 4 and trying to show the same kind of work. So I'm going to give you a few minutes to try that. Okay, so what we need to do is finish showing you the work here for this question and see if it matches your work. So we're doing negative x. So if you put in negative x squared plus y squared minus 4 times negative x minus 6y plus 27 equals 0, you can see that the x squared is going to square out and become positive. And the negative 4 and positive negative x makes positive 4x. So that doesn't match quite totally to the original formula, because if you look at it, this term is not the same. And then we're showing that you multiply by negative 1 to see if you can make it the same. And that makes everything the opposite, which means that you have the 6y now is the right sign, but everybody else is the wrong sign. So that didn't really help to make it have that type of symmetry. So both of these are no so far. So now we want to see, does this have origin symmetry? Origin symmetry allows you to put in negative for both. So negative on the x squared plus negative on the y squared. And now both of these x's are negative and the y is negative. But the 27 equals 0. So now we have x squared plus y squared plus 4x plus 6y plus 27 equals 0. And if we match that back to the original problem, the two negatives are not there. So these two terms are the wrong sign. Now if we multiply by negative 1, which is our process for checking it, we square things out and we multiply by negative 1, then that's going to make our signs right on those two question pieces, but then it's going to make the signs on all the others incorrect. So this doesn't have any kind of symmetry. So let's look at the last one. So first let's do x-axis symmetry. That means put in negative for y. So a negative on y equals x over x squared plus 9. Now you're supposed to multiply it by negative 1. So I'm going to do that to both sides to make it easier to see. I'm doing that times the fraction. And negative times negative makes a positive. And you have to stick a 1 under negative 1 so you can multiply to the top and the bottom what you have. You can't multiply negative 1 times both. So it would be negative x on the top and x squared plus 9. So that does not match, so that would be no on the x-axis. So now we're going to do y-axis symmetry, which is negative on the x. So y equals negative x over negative x quantity squared plus 9. Y equals negative x over x squared plus 9. And even if I multiply this by negative 1, which I will show, and remember when you multiply something by negative 1 in a fraction, you stick a 1 under it. That comes out correct on the top, but I end up with a negative y. So all the terms match up except the y. So it's no, it doesn't have y-axis symmetry. So last but not least, let's look at origin. So if I put a negative in for all the variables, then that will make negative y equals negative x over x squared plus 9. And then if I multiply negative 1 times both sides, and remember to put a negative on 1 over 1, because if you don't put it over 1, then you'll be multiplying the negative to the wrong spot. That makes that positive y, that makes that positive x, and that makes it x squared plus 9, and that matches the original problem, so it has origin symmetry, which is one of those rational function type problems. So it has rotated around the x-axis, and if you graphed it, you could tell that. So now you'll be able to go and do the assignment for this 1.1 symmetry lesson on Canvas.